Thank you, friends, for coming. I'll be presenting this problem before you that the Haar basis is um, two-player, one reproducible for uh, p greater than equal to 1, less than infinity. So immediately there are some questions that need to be answered. There are some terms that are unknown, especially for those who are new in this field. What is LP01? Or what are Haar bases? What is reproducibility? Or is there some game going on that we have this two-player term in there? Let's, as we tug along, we are going to answer all of those questions. So starting with what is LP01? It is a normed, complete normed vector space. So basically, it's a Banach space, and it is a space which includes all the functions f, whose norm is finite when computed by this formula. Um, what is a basis? So general definition of a basis is for any Banach space X, a sequence Xi of the space is said to be Banach space is said to be a basis if for each X there is a unique sequence of scalars for which this equation holds. And over here, the key thing is that the quality indicates that the sequence of partial sums converges to X in the norm. While we are in the definition of basis, let's look at other kinds of bases also. The first one is the block basis. So let Xi be a basis for Banach space X, Pi be a sequence of strictly increasing sequence of integers with P sub 0 as 0, and Ai scalars, then the definition of these vectors Ui given by this sum are all block vectors. Now, the sequence is called the block basic sequence. Over here, the main thing is that these blocks need to be disjointly supported. And furthermore, there are unconditional bases. So we have, let's say, Xi is a basis for Banach space as X. It is said to be unconditional if X sub pi I is a basis for X also, for all permutations of pi. And subsymmetric basis, so given a basis xi, which is unconditional. So the first thing is it has to be unconditional. Then it is said to be subsymmetric if for any increasing sequence of integers ji, the subbasis xji is equivalent to xi. So that is, if xi is a basis, then any subsequence is also its basis and it is equivalent. So let me just digress for a little bit. I want to show you guys a theorem. And why is this theorem important? Because it brings us back to the definition of reproducibility. Reproducibility is based upon this particular theorem. This theorem was given by Beseja and Pelczynski. So the theorem says that let Y be a Banach space with basis Yi, and Yi stars be the corresponding coordinate functionals. Let Xi be another sequence in the Banach space Y with these two properties. That is, it is bounded away from 0. And as this limit I goes to infinity, for all k, the action of yk star is 0. Then xi contains a subsequence which is equivalent to the block basic sequence of the basis yi. And we will see that this is going to be the foundational work for the definition of reproducibility. Okay, so why even study reproducibility? What is the importance of reproducibility? Oftentimes in mathematics, in any field, we study spaces by embedding them into another spaces. So it does two things. First of all, it might bring into light some properties of the embedded space and some properties of the ambient space. So it's no different. We are going to study the spaces by embedding them into another spaces. But this behavior is oftentimes unpredictable. Um, So how do we study spaces? We study them through their bases. Oftentimes, we identify the spaces through their bases, and it's no different in Banach space theory. Also, we would study them through their bases. So the idea is that we want to recover the basis of the embedded space in the ambient space. This is the entire idea of behind reproducibility. Can we recover the basis of the embedded space in terms of in while it is being embedded in the ambient space? And oftentimes this is very, very difficult. And so we should have some preference with basis of certain properties rather than other bases. So we could have lots of bases for the same Banach space, but uh, we would prefer certain bases because they are recoverable. They have some properties that will make them easily recoverable compared to the other bases. So we would reproduce the basis in terms of sequence of block vectors of the ambient space. So what is the reproducibility? And here is the definition. This was given by Pelczynski. A basis. So we have a Banach space X with basis Xi, which is said to be K reproducible if for every isomorphic embedding of X into Banach space Y with basis Yi, there exists a sequence of these epsilons. There exists epsilon such that for all disjointly supported blocks, ZL of Yi, we can have K plus epsilon equivalence between the basis of X and the block basis of Y. If K is 1, then we say that the Xi is precisely reproducible. So the canonical basis of C0 and LP are reproducible. This is immediate. Why? Because they are subsymmetric, hence reproducible. Let us see what are Haar functions. So here is the definition of Haar functions. So basically, they're positive on the left end of their support and negative on the right end of their support. And something else to be observed, each I can be associated with two natural numbers, j and k. And here is the picture of some of the Haar functions. So h sub 0 is the constant one function. H1 is, as usual Haar functions as defined earlier, that it is positive one on the left end of the support, negative one on the right hand of its support, H2, H3, and something else to observe. Now, when we get to this level, this is the second level of the Haar functions. So second level tells you that there are going to be, so this could be considered as 2 to the power 1, the first level of the Haar function. So we would have 2 can be written as 2 to the power 1 plus 0. That's why this is the first level of the Haar functions. So 2 to the power 1 is 2. So there should be 2 Haar functions in this level. And the support of each of them is 1 over 2. And that's what this is telling us, that each I can be associated with two natural numbers. And then we would also define at the level of Haar functions is given by this J. And if they're on the same level, their supports are equal. If they're not on the same level, then there is this relationship based upon J1 and J2. We would denote the support of the Haar functions by this uppercase EH phi JK. Something else, that the Haar sequence is a monotone basis for LP01. H sub I is unconditional for p greater than 1, less than infinity, and for p equal to 1, that is the Haar basis, is conditional. Okay. Something else that needs to be said, that the closed linear span of the subsequence H sub 2i of Hi is isometric to little lp, and hence Hi is not subsymmetric to LP01. Okay. Haar basis is not subsymmetric. Of course, for L1, the reason is it's not unconditional. But for the other ones, observe that this subsequence is not equivalent to HI. So we needed the subsequence to be unconditional basis needs to be equivalent to the original basis for them to be subsymmetric, but that's not the case. So hence it is not subsymmetric even for this. Something else that we will observe is that reproducibility is the necessary condition for subsymmetry, but the subsymmetry is only the sufficient condition for reproducibility. That is, anytime I have a basis that is subsymmetric, then it will necessarily be reproducible, but not the other way, as Haar basis is going to prove. It is not subsymmetric, but it is still going to be reproducible. So reproducibility, anytime we have a subsymmetry, we definitely know it is reproducible. But there are bases that are reproducible, not necessarily subsymmetric. Okay. So before we move on, we are going to introduce this this theorem given by Gamlin and Goddard. What they did was they found Haar-like functions. They are defined having values -1, 0, and 1, just like Haar functions. And at each level, again, the support is decreased by half. The number of Haar-like functions doubles. In our case, case of 1 and case of 2 are 1. So it's just going to be that these are just like Haar functions. The only difference, and this is the important difference, is that Haar-like functions are defined on Haar functions are defined on dyadic subintervals. But that's not true for Haar-like functions. They could be defined on any set of positive measure. So doesn't have to be dyadic subinterval. So then if we have this, Haar-like functions are equivalent to Haar functions. That's all what this is saying. So now let's get into the game version of the proof of reproducibility of the Haar basis. So the game version of requires that we define what are the rules of the game. First of all, this game has two players that are playing the game. And then these two players play alternately. And player 1 begins the game by picking up a natural number. Player 2 does two things. He has to find a vector from the embedded space and then a block vector from the ambient space, fulfilling the conditions depending upon what version of the game we are playing. And then if player 2 is successful in picking up the vector from the embedded space and the block vector from the ambient space, fulfilling those conditions, after every move of player 1, then he wins the game. And there are infinite number of moves for each of the player. So let's begin with the very first definition that we have of a two-player reproducibility game version. This is called the subsequential reproducibility. This definition was provided by Aspech and Sari. Here's the definition. So let's say we have a Banach space X with basis Xi and Banach space Y with basis Yi. We embed X into Y via an isomorphism. And then if for every sequence of epsilon i's, we can find a subsequence TXI J's and DXILs and WLs, DXIL, where XIL is in the embedded space and WL is the block, is a sequence of block vectors of the basis Y in the ambient space, fulfilling these two conditions, then we say that Xi, the basis of the embedded space, is sequentially C reproducible. whatever this constant is. Now, when we compare it to the former definition or the original definition of reproducibility, here are some of the things that we observe. First of all, we see that T is uh, not isomorphically isometric, but T is only isomorphic. Uh, Something else that should be said, um, we are able to reproduce the basis of the embedded space is accomplished through the sub-basis of the embedded space. So the basis is equivalent to the sub-basis, and the image of the sub-basis is equivalent to the block basis. So the original basis is equivalent to the sub-basis, which in turn, by perturbation lemma, is equivalent to the block basis of the ambient space. So we accomplish the same task of having the basis of the embedded space reproduced as the block vectors of the ambient space. So we show that the Haar bases do not possess this strong subsequential reproducible property. To this end, what will we do? We will find a subsequence of the Haar basis, which will fail to fulfill either of those conditions. And recall that, first of all, any disjointly supported sequence of functions, its closed linear span is isomorphic to little LP. So our goal will be to find a subsequence of the Haar basis, which is equivalent to the disjointly supported subsequence of the Haar basis. So let's do it. So we'll prove, first of all, this proposition. And after we prove this proposition, we'll use it to prove that the Haar basis is not subsequently C reproducible. So here is the proposition. HI is normalized Haar basis of little l of LP be greater than or equal to 1 less than infinity. Then for all sequence, then for all epsilon greater than 0, we could find a subsequence of natural numbers ni such that for all mi fulfilling this condition, their corresponding normalized Haar functions are 1 plus epsilon equivalent to the unit vector basis of little LP. So here is how the proof begins. That epsilon L be greater than 0, and we pick a sequence of positive decreasing numbers epsilon I such that their sum is less than epsilon. Recall that the measure of the support of any Haar functions is basically 1 over 2 to the power Li, where Li is giving us the level of the Haar function. Okay. So for every L, pick NL fast enough so that for the sequence of MIs fulfilling the inequality, we have this property of their associated normalized Haar functions. Their support is, the measure of their support is less than this number. Now, why this is the case? We could choose such because remember that the measure of the supports of Haar functions is going towards 0. Why is this necessary? Because remember, we want to disjointify a function, sequence of functions. And so once we have a disjointly supported sequence of functions, its closed linear span will become isomorphic to LP. And then we will show that these are going to be equivalent to the this sequence would be equivalent to the unit vector basis of little LP. Okay. Here is how we do that. We have this ML for this arbitrary sequence. The values of the Haar functions, because these are normalized, will be these. Our goal is to show that these are 1 plus epsilon equivalent to the unit vector basis of LP. So we disjointify H sub ML. Here is the disjointified function. So since it is disjointified, its closed linear span will be isomorphic to LP. We want to compute this difference. Let's see that this difference is less than epsilon L. And here it is. Over here, the The only thing that probably needs to be mentioned over here is maybe two things. First of all, we see that by the definition that the difference would be equal to this. Over here, we are looking at union. So when we look at the union, it is smaller than when we sum up all the supports. So, and then when we pull out the sigma, it would be less than equal to this. Well, the next step is just the computation of our integration. And over here, we are saying that why this is the case, that this is greater, because R is any, R is going to be just greater than any L. But we are just saying, okay, going from L to L plus 1 to L plus 2. Now, the next approximation is greater because we are replacing the numerators by a bigger number, because epsilon L is a sequence of decreasing positive numbers. So we are replacing them by epsilon L's, all of them. And then the denominator is made smaller. Okay, so when we factor this out, we get this. Okay, so now we have that there's the sum of the difference of the, so some of the norms of the difference of the function and its disjointed counterpart is less than epsilon. So because sequence of arbitrary scalars such that their pth norm is equal to 1, and then we will have by the triangle inequality, this one would be satisfied, and by the reverse triangle inequality, we would have this. And then when we combine that, we would have that HML is equivalent to the unit vector basis of little LP. Okay. So now we have seen that we have this sequence HMIs, which is equivalent to the unit vector basis of LP. So here is our proof that the Haar basis is not two-player subsequently C reproducible. So we take T to be the identity map, Y to be the, again, LP01, and we embed LP01 into LP01 using the identity map. If player 1 chooses this N sub L lacunary sequence, and the second player chooses this sequence HMI, then we know that HMI is equivalent to unit vector basis of LP. Hence, it is not equivalent to the HI. So it fails the second part of the definition. HI is not equivalent to its sub-basis HMI. So we have that the Haar basis is not two-player subsequently C reproducible. Now we show that the Haar basis is two-player, one reproducible, but using blocks. That's the difference. Here is the definition. Again, this is two-player C reproducibility. So the definition would be X is a Banach space with basis Xi, Y is a Banach space with Yi. We embed X into Y using an isomorphism. Epsilon L is a sequence of decreasing positive numbers. Then Xi is said to be two-player C reproducible if the second player is able to find these vectors UL in the embedded space and block vectors WL of the basis YI that are fulfilling these two conditions. And again, the idea is UL is equivalent to Xi, and we have that the image of UL is equivalent to the block vector. So again, we have the same setting. The basis equivalent to its block basis, or the vectors UL, and the vectors UL, their image is equivalent to the block basis of the ambient space. And here is what is being said when we compare it to the original definition. What do we find? That T is an isomorphism, not an isometric isomorphism. Haar basis fails to be reproducible through its subsequence. So the original basis is equivalent to its block basis, which in turn, by the perturbation lemma, is equivalent to the block basis of the ambient space. So before we even move on, Here is the lemma that is needed. Observe that the Rademacher sequence, whenever it is restricted to any dyadic subinterval, is weakly null. And any isomorphic image of a weakly null sequence is weakly null. So it would be that D, when we look at the image of these Rademachers, they are going to be equally weakly null also. So here is the theorem. We show that for p greater than equal to 1, less than infinity, the Haar basis hi of LP01 is 2-player 1 reproducible. So we start with picking up a sequence of decreasing positive numbers, epsilon I, y be any Banach space with basis yi, tv, and embedding of LP01 into y. So the second player starts the game by picking up a number n sub 1 in the set of natural numbers. What would player 2 do? Player 2 has two things to do. First of all, he's going to pick a block vector u1 in the embedded space, and then he's going to find a block vector in the embedded space. And the difference of two needs to be less than epsilon 1. And here is how he's going to do that. Observe the first vector that he needs to construct is h sub 1. H sub 1 is is positive on half of its support and negative on half of its support. And when we look at any Rademacher sequence, it is positive on half of its support and negative on half of its other support. So that's what this is saying. And any Rademacher sequence is basically summing up all the Haar functions in I-1 level. And that's what this is saying. So we want to construct the first one. Observe that it should be the sum of all the Haar functions in this n sub 1 level. And we pick n sub 1 in such a way that it is supported after n sub 1. See that each one is positive on half of its support, negative on half of its support, and here I have R4, but any Rademacher function could do that. All we want is that T sub U1 is supported after capital N sub 1 because it is embedded in the space Y. So there are sequences of scalars for which it can be expressed in terms of yi. And we cut off the tail such that the difference is less than epsilon L. We define this as the block vector W1. And we are finished with the first stage. Suppose that L stages have been completed. So the numbers N sub L and M sub L has been picked. Suppose that the first player picks N sub L plus 1, which is greater than M sub L. Then player 2 has, again, the same responsibility of picking up a block vector U sub L plus 1 in the embedded space and to find a block vector in the ambient space. So the entire thing is that this block vector that is chosen in the embedded space its image must be supported after N sub L plus 1. That's the only thing that the player has to be aware of. And this is what we do. We look at this vector. Its picture is like this. And you can see that any Haar, any Rademacher function that is restricted to the support of this Haar function would be able to accomplish this. And again, because this is a term in the space Y, so it can be written in terms of the basis yi with some sequence of scalars. And now we pick M sub L plus 1 large enough so that the tail is very small. We define this as our block W sub L plus 1, and we have completed this stage. Now, by our choice of vectors, the block vector from the ambient space and the block vector as we've defined of the ambient space, the first condition of the definition of reproducibility is fulfilled. But then for the second one, observe that this computation tells us that the vectors that ui are isometric to the vectors hi. And hence, we have that HIA is 2-player, 1 reproducible. Thank you for coming, folks. If there are any questions, they are welcome.